Welcome back. So in this course we have of course covered many things mainly at a fundamental level, and we have covered kinetics, different mechanisms by which reaction happens for different kind of fuel and mixtures. We have covered different kinds of flames, non-premix flames, premix flames, their ignition extinction behavior, but all of those are at a laminar level. So, we really have not brought flow into the picture, but as you know that combustion, a large part of combustion is also flows. Okay, it's as a combustion is essentially chemically reacting flows with large heat release. Okay, so and especially in an engine, flow is the type of the flow, the nature of the flow has a very important effect on the combustion behavior. The most important thing, most striking feature of the flow, apart from the different kind of patterns etc. that is formed, is that in an engine the flow is invariably turbulent. Why? Because you see engines operate by the principle, aero engines operate by the principle of thermodynamic cycles. Say most important among them is the Breton cycle. Now in the Breton cycle, if you see that before you extract work, the heat addition process is essentially a constant pressure heat addition process which happens at high pressure. Okay. So a combustor in an engine is invariably at much higher pressure relative to the surrounding ambient pressure. Okay. Now that pressure can be different for different engines. For example, in a gas turbine engine the pressure can be 30-40 bar in a or 30-40 atmosphere. In a scramjet engine it can be of the order of 1, 2, 2, 3, 4, 5 atmosphere. Okay. In an afterburner it can also be little low pressure, but the fact of the matter is that in all these cases the engines operate at very high flow rates and they are at high pressure, and the resulting effect is that in engines, in gas turbine engine, in scramjet engine, in afterburners, in ramjet engines, all aero engines, the flow is intensely turbulent. Okay, the flow is intensely turbulent. Please keep this in mind. An engine flow is intensely turbulent. So the combustion process, associated combustion process that happens is also is a very strongly turbulent combustion process that happens. Okay. Now what does turbulence do to combustion? That is a very difficult question, because turbulence itself is a complex process and combustion also itself is a complex process. So when they meet, the resulting process that emerges of turbulent combustion is actually very complex. But for that we need to understand basically the flows in an engine, we need to understand turbulence at a very good level, we need to understand combustion at a very good level, and also then after that we have to understand how turbulent combustion behaves. So far we have basically developed an understanding of combustion. Now we will develop an understanding of turbulence, then we will go to turbulent combustion, and at that point we will be in a very good situation to take up actual processes that happens in a different kind of aero engines. So that is how the course is structured. Okay. So we slowly build up complexity, we slowly understand laminar combustion process, we slowly understand turbulent combustion process. So then we understand how they interact and what is the resulting interaction that emerge, and then we understand how it behaves in an actual engine. So this is the whole story about this course. Okay. So you see that in engines, in aero engines, the turbulence Reynolds number, which we can define as essentially U prime times U prime means a U RMS, say U prime RMS, rather the RMS of the fluctuating component of velocity, times a characteristic length scale which can be the diameter of the engine, or divided by the kinematic viscosity, that is of the order of say 50,000 in a gas turbine engine. It is of the order of 10,000 to 5,000 in an afterburner or a scramjet engine. But this is turbulence Reynolds number, this is not just normal Reynolds number. So invariably all flows are very, very turbulent, and we need to understand turbulence as well as combustion, which we have understood combustion already at a good level. We have not talked about turbulence. So in this class we will talk about turbulence, and then we will utilize these concepts to go into turbulent combustion and different modeling approaches. Okay. So, then this we come to module 9 where we talk about combustion in turbulent flows. So, as you see that this is organized in this manner, that combustion in turbulent flows will first go into introduction to turbulence, will go into Reynolds averaging, will go into like turbulent kinetic energy, and then we go into different closure problems and models. And majority of this material, now we go to a different book, will mainly follow like Stephen Pope's book published by Cambridge University Press, and we will consider also turbulent combustion, the book on turbulent combustion by Norbert Peters, which is also published by Cambridge University Press. So, for this part, from this part onwards until we go to engines, we will essentially follow these books. Okay. So, turbulence part will mainly follow Pope's book, and turbulent combustion part will follow Peters's book. So, that is how it will work. Now, turbulent flows. Of course, turbulent flows are ubiquitous in nature. We can find turbulent flows everywhere. Say the smoke coming out from our chimney, a large chimney is invariably turbulent. Okay. And the most important characteristics of the turbulent flow that we find is that it is strongly dependent on Reynolds number. Okay. At least in visually, we will see what that actually means. So, we see that if we see this turbulent flow, the structure, we see that the overall, if we consider these two jets, okay, at essentially at two different Reynolds number, we see that the structure, overall structure is not very different. Yes, the jet is essentially diverging. Okay. So, this jet is diverging like this jet is diverging like this, and it is not very different on the overall thing. But what is different is that the scale, the smallest scales of this jet are very different at different Reynolds number. So, you see that here of course, this different kind of structures are formed, but the smallest scale of this structure is say of this scale, whereas the smallest scale is that it is very small here. We cannot even show it by this thing. Okay. So, we see that as Reynolds number increases from 2300 to 100 to about 10,000, the small scales of this flow become smaller and smaller. Okay. And that is actually an universal property of turbulence. As you increase the Reynolds number, the smallest scales become smaller and smaller. Okay. It develops more and more fine scale structures. Okay. So, this is one of the most important things. And then we talk about combustion. Okay. So, this image, this very visually attractive image shows the different states of combustion. Okay. So, the first one is essentially, all three are essentially expanding flames which are ignited by a pair of electrodes at a center of a volume which is filled up by fuel air mixture. So, you have essentially a big volume inside a ball, okay, and then you fill up that volume with fuel air mixture, and then you ignite it with a spark, like something like what happens in a engine. Okay. And then of course, the flame will propagate, it will consume this surrounding fuel air mixture and it will convert them into products. So, this is essentially fuel plus air mixture, and this is product, okay, the inside of this flame. But so, this happens in time. So, you see that this shows the different structures of a flame that we can expect. This is what happens in a laminar flame when there is no difference in flow. This is when there is, you have this pressure is very high and the flame develops this intrinsic instabilities. This is called the Darius-Landau instability, which we will not cover in this course. And this is when the surrounding flow is turbulence. Of course, you cannot see turbulence because you are only visualizing this flame by the Schlierian imaging, which gives you the density gradients, or the second which essentially gives you the density gradients. So, but you see that when you have turbulence, this nice symmetric shape of the flame is lost and it develops these different structures on these things. And of course, as you can think that just like the jet, if you increase the Reynolds number in this case also in this turbulent premix flame, the size of the structures will become smaller and smaller. Okay. So, this is also a very striking part. So, here we see that how exactly turbulence disturbs the flame's front to create this different kind of structures on the flame. So, this makes these different scales of different or the structures at different scales and interaction and the flame propagation at depending on these different structures makes understanding turbulent combustion very difficult, but this is what is happening in an engine. In an aero engine, a flame looks something like this. It does not look like this. it does not look like this, it looks something like this. Okay. So, this is what is happening in an engine, and we need to understand this, and for that essentially we can consider at the first level, we can consider that the turbulence disturbs the flame structure, but by causing perturbations at different length scales, but it is more than that. Turbulence actually can go inside the flame structure to disturb it also, but we will come to that in different times. Now, here are some examples of combustion in turbulent flows. Of course, we have seen that this is what happens in an engine, this is what happens in this volume. So, this is you see this is essentially the kind of an gas turbine combustor, where you have the swirling flow and this you see the different kind of turbulent structures coming out, and you can have in nature also you can have turbulent combustion in form of wildfires, and in an engine of course you see that turbulent combustion is happening inside the combustor. So, if this is an aero gas turbine engine, and this is its intake, which is followed by the different stages of compressors, okay, and then this compressed air, this is the track of the compressed air of the compressed air, and then it enters into this combustor, and then it goes into the turbine, and then it goes into the exhaust. Okay. So, the combustion can happen here, and then if you have an afterburner here, it can also happen here. Okay. So, in this case there is no afterburner of course. Okay. So, this is the thing, so this is the entire combustor might look actually small, but actually the thing is that this is the point where you have the highest pressure. Okay. So, this is the point where you have the highest pressure. So, of course, when the flow is compressed, it occupies a very small amount of area. So, that is why it occupies a small volume. So, that is why it is small, and so these are the different examples of turbulent flows in different engines. Now, once again going back to turbulence, of course, turbulence is a complex thing. Okay, and even Heisenberg, whom you know that is famous for this uncertainty principle, and when asked about turbulence, he said that when I meet God, I am going to ask him two questions. So, why relativity and why turbulence? I really believe he will have an answer for the first, that is, he will have an answer for relativity, but there is no answer for turbulence. So, turbulence still is the most important unresolved problem in classical physics, okay, and it still continues to be like that. But the thing is that of course, it is very beautiful, it has got its numerous beauties in terms of understanding mathematics, physics, etc. The dynamics is very beautiful and complex, but when you have combustion, then it makes even more complex object to look at. But the thing is that this is what is happening in an engine, so we need to understand it. Okay. So, now as such nearly all macroscopic flows occurring in nature and engineering devices are turbulent, and the turbulence may be simultaneously problematic and beneficial. For example, you know, the turbulence leads to increased drag on surfaces, okay, it leads to loss in efficiency, but at the same time by the same reason it also has a higher heat transfer rates. So, which enhances heat transfer. And of course, in an engine, turbulence enhances mixing in air breathing combustion engines, okay, and of course you want mixing is very important, because after you inject the fuel, if it is not injected in a premixed state already, after you inject the fuel, you need to have a quick mixing so that combustion can happen, okay. So, that turbulence can enhance that, and it enhances mixing in air breathing engines, okay. So, how do you define turbulence? Okay, turbulence is not easy to define precisely, however, it exhibits the following generic characteristics. Okay. Now, what are that? First most important characteristic is fluctuations. These fluctuations make turbulent flows look irregular, chaotic and unpredictable, even though turbulence is not entirely random. Okay, it is not if you say for example take a velocity probe, a hot bed anemometer, and stick it into a turbulent jet, you will get signals which are fluctuating, but it is not noise, okay, because noise, if it is not random noise, has zero correlation. Okay, that one point to the next point, there is no correlation among them, whereas in turbulence there is a finite amount of correlation between the velocity at one point at first data point and the velocity at the second data point. Of course, it changes, okay, so the correlation is not infinite, it changes, but at the same time it is not exactly noise. Okay. Then you have nonlinearity, okay, flows change state drastically beyond the critical numbers, that is if you consider a pipe flow, the Reynolds number is about say below the critical Reynolds number, the flow behaves like one, after the critical Reynolds number the flow behaves like another. Vorticity, yeah, vorticity is very important in turbulent flows. It's very much rotational, and range of eddy sizes increase, and the range increases with Reynolds number. So if you go back to the to this picture, you see that the range of eddy sizes increases with Reynolds number. The meaning is that the largest size eddies is of the order of, say, this scale. Okay, so which is also the same here. It will be of the order of this scale, but here the smallest size eddies is of the order of this scale, which is say this. Whereas in this one it's very small, can be of the order of even smaller than this. Okay, so that is what we are talking about. So as the Reynolds number increases, the range of these eddy sizes, the range of this rotational coherent structures essentially increases with the increasing Reynolds number. So that is a very important and striking feature of turbulence. Okay. Dissipation, that the energy at small scales, that you will see later that there is a continuous cascade of turbulent kinetic energy over different scales, and ultimately it is converted to thermal energy, and it is converted to thermal energy by the effect of viscosity. So to maintain turbulence you need to have a continuous supply of energy, and we will see that how even the flow itself can provide as a supplier of this turbulent energy, turbulent kinetic energy. And then you have diffusivity, so you have rapid rates of mixing and diffusion of the species, momentum and heat. So some people can think that you can think that there is an enhanced amount of diffusivity in this enhanced diffusivity in this when there is turbulence. Okay, and as such that there are some flows that might seem random, such as wind driven ocean, but that is the surface waves are not essentially turbulent. It can be turbulent under certain conditions, but just when you see some fluctuations and random, that does not mean that that is turbulence. So turbulence has its own characteristics which we will show now. Okay. So one thing is that, of course, where does turbulence come from? Turbulence comes from the momentum equation, right, the Navier-Stokes equation. The reason is that the Navier-Stokes equations are nonlinear, because it's, you see, the convective acceleration term, which is that v dot divergence on v vector, that is there is a nonlinearity in v. So this turbulence essentially stems from that term itself. Okay, so it is that nonlinearity that makes turbulence nonlinear. Okay. Now the question is that if the governing Navier-Stokes equations are deterministic, why is it solutions, that is turbulent flow, appear random? The reason is that just like any other nonlinear systems, of course turbulence is one very important nonlinear systems. The turbulent flows are actually sensitive to perturbations in the initial condition, boundary condition and material properties, and of course that is what creates this. So if the proper design and careful effects, these perturbations can be reduced, but they cannot be eliminated. Okay, and perturbations are even present in laminar flows, but at high Reynolds number of turbulent flows, the flow field is extremely sensitive to small changes. So one small change can result. So you have the same initial condition. Suppose your initial velocity at the inlet is v is equal to 10 meters per second in one case, and in another case it's at 10.2 meters per second. And this small difference of the velocity, inlet velocity, can actually cause a different kind of turbulent structures. Okay, the statistical properties may not be very different. That is, the average properties may not be very different, but the instantaneous properties can be widely different, and that is very natural, because when a flow enters into an engine, you have absolutely no control whether the velocity will be, say, 10.1 meters per second. A particular velocity at a particular point will be 10.1 meters per second or 10.2 meters per second. So the flow itself is turbulent. Okay. So the thing is that this can be appreciated by if we consider this Lorentz system, that is the effect of turbulence being like chaotic like this is because of the fact that turbulence is the governing equation, is a nonlinear partial differential equation. So if you consider this nonlinear equations like this, that if you consider this Lorentz system, that is where is given by x dot, y dot and z dot, whereas this is a coupled set of systems which itself depends on y and x, etc. So in this case you see that the solution for a given sigma, which are essentially constant, beta and rho, if you have this this kind of set of initial conditions x0 at time t equal to 0, you basically then solve it over time, this Lorentz system. You see that at x with initial conditions of x at time t equal to 0, y at time t equal to 0, z at time t equal to 0, if there is a 0.1, 0.1, 0.1, okay, then we get one set of solutions. Now if we change it to this 1, 2, 3, 4, 5, 6, 7, seventh place of decimal of this thing, okay, and you get a solution which is initially it stays same, as you see up to this point it stays same, but then this difference starts happening. Okay, so then if you plot this difference, that is this is the x t and x prime t. The only difference between these two the solutions is the fact that the second one, the initial condition of x has a difference of the 7th place of decimal, okay, in this thing. So you see that the difference builds up, and this difference is of the order of the actual solution. So this, after some time, there is no resemblance between at least instantaneously there is no resemblance between these two solutions. So you see that this type of coupled equations, when you have differential equations governed by differential equations, when you have these kinds of things, any small perturbation in the initial conditions can result in different solutions. So that is why the whole purpose of turbulence is not to predict instantaneous structures or instantaneous velocities at a particular point. Rather, we will predict, we are interested in predicting the statistics. Okay. So that is why while neither the deterministic nor statistical analysis have been able to conquer details of turbulence, the statistics do offer useful tools for understanding turbulence. So the whole purpose is to understand the different statistics of turbulent flows, either for turbulent non-reacting flows or for turbulent combustion, etc. So we are interested in understanding the statistics of this turbulent flows. Okay. Now the most important thing we will go here to understand about statistics is that the first point to note is that we will talk about Reynolds decomposition. So if you have a turbulent field quantity, which can be anything, velocity, temperature, pressure, etc., species, etc., we can resolve it into mean, its average, and fluctuation. So u is essentially equal to mean u plus and small u, which is the u fluctuation. Okay. So we will come to this, what actually these are and how to get this. We will discuss this in this class. Okay. So now if you see this thing, that averaging of the mean depends on the nature of the term, and we will talk about averaging, but what particular averaging we are talking about depends on the particular application at hand. So we will consider a temporal average when, say, u is stationary in time. We will consider spatial average when u is homogeneous in space. Okay. But this we will basically consider a generalized averaging, which is ensemble average, when arithmetic average over which is essentially arithmetic average over independent realizations under identical conditions. So essentially you perform the experiment different times, and for each experiment you measure some particular quantity, and that essentially becomes ensemble average. So it is not exactly temporal average or spatial average, but of course this can correspond to those things under particular situations. So we will go into Reynolds average Navier-Stokes equation, and for that to develop that understanding we will basically have to develop some statistical parameters which will come useful in this course also. So I hope that you have some basic introduction to statistics, but I will just for the sake of completeness I will just recapitulate some of them here. So first, in this introduction to turbulence, we will not consider density variation, though the purpose of this course is to understand turbulent combustion, but just to introduce these concepts in a simpler manner, we will first just do we will consider the Navier-Stokes equation or the continuity equation or other equations without considering any combustion. So, but eventually at in the later part of these lectures we will introduce density variation, and we will consider the full equations with complexity. Okay. So first we will just start with equations, continuity equations and momentum equations for a non-reacting isothermal constant density turbulent flows. Okay. So that is the thing. So essentially first we will consider non-reacting flows without density change. So the momentum equation or the Navier-Stokes equation under certain such condition becomes dou uj dou t d capital, this is material derivative, rho times density times d uj dt, which is the full material derivative, is essentially the partial of the stress tensor along x direction. Okay. Whereas this tau ij is given by this is actually G. So, this is actually dou T dou ij by dou xj, whereas this tau ij is given by minus P times del ij. P is the pressure, dij is the Kronecker delta function. So, I introduce the tensor notations here, times mu times dou ui dou xj plus dou uj dou xi. Repeated indices means addition, for example in this case. So, it is addition over sorry, this is actually I. This implies So, this is the Navier-Stokes equation. Okay. Now, let us define the concept of probability.